Hello, everyone, and welcome to the 46th Surface Ventures keynote webinar. It'd be great if you could say hi in the chat and tell us where you're joining from. It's always great when we can see where you're all from and yeah, the various places that you're from. My name is Dr. Sam McMaster. I'm the content manager at Surface Ventures. We are a not-for-profit organization, and our mission is to provide world-class surface and materials science education for both academia and industry. Today, it is my pleasure to introduce Dr. Janet Wong of Imperial College London. Janet Wong is a reader in Tribology and Mechanochemistry in the Tribology group within the Mechanical Engineering Department at Imperial College London. She's a specialist in interface phenomena, additive technology, and nanotribology. She has pioneered the application of fluorescence spectroscopy and imaging, which examine in situ lubricants at tribological contacts. Her research focuses on additive film formation and lubricant rheology in order to enhance machine durability and lubricant performance. And I'd like to thank today's partner, PCS Instruments. Later in the event, Dr. Kieran Nair will be joining us to deliver a presentation on the various offerings from PCS Instruments. We'll also be releasing poll questions and handouts from PCS Instruments throughout the event, and I'll highlight when those will be releasing in the chat. As we go along, please type your questions into the chat and they'll be marked for the Q&A sessions later in the events. That will be after both of the presentations. We're planning to go for around 60 minutes in total today, and we'll be sharing a link for your attendance certificates later in the event. So that will be shared at the beginning of the Q&A session. Okay, so without further ado, let's welcome our speaker to the stage and proceed with the webinar. So Janet, you could please come on stage. Welcome, great to have you.
Okay, so let me
just get you set up with your screen share. We'll be beginning the presentation in a moment, everyone. Okay, fantastic. I can see your screen, and there we go. PowerPoint is full screen. Please take it away. Thanks.
All right, thanks, Sam. Hello, everybody. My name is Janet Wong. I'm from Imperial College. For the next 30-40 minutes, I would like to share with you some of our recent research looking at how the atmosphere affects the tribology of steel-steel contacts. This work is actually done in collaboration with my colleagues, Jason Zhang and also Professor Hugh Spike, and is partly funded by Shell UTC and also with the help of PCS Instrument. So a lot of us here probably are familiar with the use of lubricant to reduce friction and wear in tribological contact. In some cases, the use of oil is not suitable. Perhaps you're worried about contamination or your operating condition is of high temperature. So in those cases, you might choose to have the contact in dry condition. However, even in the case of dry condition, chances are, it's not like there's nothing around the contact. In a lot of time, there will be gas around it. It can be air, or you can, have your contacts in an encapsulated condition in nitrogen or in argon. But in all those cases, there is a chance that all these gaseous molecules could potentially interact with the surfaces. So that basically means that we need to understand how this interaction potentially affect the tribology of our contact. So here is just some example that the gas environment may be important for tribology. For example, you might be dealing with air bearing, or you are in gas processing. Refrigeration is obviously an important scenario for that. And some of us here may be looking into the use of hydrogen and ammonia for internal combustion engine. So in those cases, again, the effect of gas and its interaction with the surface is of importance when we care about the tribology of this contact. So the study of how gas interact with surfaces are not new. It has been around for a while, especially if you talk about gases such as oxygen and dry air. Obviously, if you are focusing on steel, then we all understand why air and oxygen is important, because you create oxide as a result of that. So the literature has shown that, depending on the oxygen content, your steel contact actually could have better or worse friction and wear. But it also depends on the material property of the steel as well. For example, like hardness is one important property to consider. Other gases, for example, like inert gases, it has been studied a lot actually. For example, like argon and helium, most of the work has shown that they are not beneficial in terms of reducing friction. Hydrogen is also one gas that has some study as well, and because of the reducing nature of hydrogen, most work have shown that hydrogen is not good for friction and wear. In terms of nitrogen, some work show some reduction in friction and wear. There is some speculation that it is because of the production of nitride on metal surfaces in a nitrogen environment, but the evidence here is a little weak. But that's basically a conjecture of why nitrogen could potentially be helpful. Then there's also work on carbon dioxide. In this case, if you look at the literature on carbon dioxide, you see work that say it is useful. There's other work that say that is totally not useful at all. It seems like for the effect of carbon dioxide, it's really condition specific. And there's also other work as well. For example, like I have mentioned here on the chlorhydrocarbon, some work does show that it is useful. So far, the work that I have stated here are mainly looking on steel. Obviously, some of us also work on other surfaces as well, and there are works looking at the effect of gases on other material as well, but it's not as much as looking at steel. One of the thing that I find quite interesting is that I find some work that is looking at the effect of coating on steel. And specifically in this piece of work, they use a vanadium nitrogen nickel coating on steel. And they found that if you have this coating, then methane actually is good for reducing friction and wear. But without the coating, methane is actually not good for steel. So basically it's suggesting that if you modify your rubbing surfaces, then potentially the gas in the environment may react through catalytic interaction, and therefore it gives you a more beneficial tribological performance. And again, there's also other work on other material as well. When I look at the literature, one thing that I notice is that if you think about what we face now, there's this interest in looking at, for example, ammonia in IC engine or hydrogen. There's not a lot of work on those gases that are more dangerous or poisonous or flammable. And there is a reason for it, because if you want to run tribological tests in this condition, you really need to think about risk assessment, right? And obviously you don't want to put your life at risk or your student or your colleague's life at risk. So how are we going to run experiment on these gases so that we have a good understanding of how our contact would behave in this condition, but do it safely? So luckily, we work with PCS very closely, and when we spoke to PCS about what we want, they actually come up with a solution. So the idea is actually quite simple. So they have a machine which is called the high frequency reciprocating rig. So in a nutshell, what it involves is just a sphere which is in reciprocating motion and is pressed and rubbed against a flat disc. So with this contact, what happened now is that we are going to put this in a stainless steel enclosure. So this stainless steel enclosure basically allow us to, inject gas into the barrel to make sure that now the rubbing contact is completely submerged in the gas that we like it to experience. The important thing here really is that the vessel has an internal volume of about only 20 milliliter. So you can imagine that even if we are dealing with a relatively dangerous gas, the volume of gas that we need to deal with is relatively small, and the whole machine is actually quite compact. So we can put the machine into a fume hood, and we only need to deal with a very small amount of gas, and that is actually what allow us to run these tests in hydrogen or in ammonia or in methane relatively safely. So this machine also allow us to run experiment up to 130 degree and to 10 bar. But for the result that I'm going to show you, we are just going to do it in room condition, room temperature and in 1 bar. So as I said, we are going to look at the effect of the gaseous environment on the tribological behavior of steel-steel contact. So here is just to show you what is the test condition that we use. And we try many gases here really, because this is for us more like a scouting exercise to understand what gas is actually more beneficial and what gas isn't. So I grouped the gas into 2 groups. The first group you can see are the more conventional candidates. We have the air and oxygen with the inert gases, nitrogen, which is relatively inert, hydrogen, which is reducing. And then there's also some gases that we think potentially may be interesting here. For example, ammonia, carbon dioxide, and carbon monoxide. The other group of gases here are all hydrocarbon gases. So you can see that here we have a group of saturated hydrocarbon, and they are basically from very short chain. So this is CH4 all the way to a slightly longer chain. So in this case, we have 4 carbons. So you have 1, 2, 3, and 4 carbon chain length, and they are saturated. And in here we have hydrocarbon now, which is not saturated. They are unsaturated carbon. So we have this, which is 2 carbon molecule, but it has a 1 double bond. This is a 3 carbon molecule with 1 double bond, and then you have one which has a triple bond, but two carbon. So let's see how these gases behave. So the first group I would like to show is the inert gases. So you can see that all of them actually have a friction coefficient of about 1. So if you think about steel contact in vacuum, so this, and you rub, so this is basically roughly the friction coefficient you get. So what is showing here is that the existence of these gases has no benefit at all, and the friction coefficient is so high, it's basically suggesting that you probably have adhesive wear in this case. So let's see what happens when we now subject the contacts to air and oxygen. So the literature say that we should have slightly better performance. And as you can see, the nitrogen, which is in a kind of purple color, and also the dry air, which is in the light blue color, they are a little bit lower than what we have obtained in argon, helium, and hydrogen. So this is basically similar to what the literature has found. If we look at the amount of wear, which is shown in the bar chart, so I need to explain to you a little bit about what the bar chart here is showing. So the orange dot here is basically the friction coefficient, and the blue bar is the average wear scars of on the ball. So the larger the wear scar, meaning that the more severe the wear is. You can see that all these gases has similar friction coefficient, but the one with dry air and oxygen has slightly lower friction coefficient as shown in the graph as well. But for the wear, you can see that now for oxygen and dry air, you get much higher wear. And that's basically what you would expect at high oxygen condition. You are going to have much more severe oxidative wear, and that is why, despite the fact that their friction coefficient is all around 0.8 to 1.2, but when there is large amount of oxygen, your wear is way more substantial compared to the case when you actually are in more inert condition. So now let's move on to look at other gases. So here we have carbon dioxide. We can see that in our case, carbon dioxide actually is performing worse compared to air and oxygen. In fact, it is behaving like when the contact is in inert gas and hydrogen. So again, as I've mentioned, the performance of carbon dioxide really depends on condition of the test. So our condition is just such that it is not helpful. On the other hand, if we look at the effect of carbon monoxide and ammonia, now it's actually very interesting. We show that these two actually give you, a reduction in friction. In fact, if you look at the friction coefficient of ammonia, 0.2 is really not bad. If you think about using organic friction modifier in oil, you get about 0.1, and here you are rubbing dry, and so this is actually not a bad number. So let's just take a look at the wear. So you can see that for these three gases, the wear and the friction correlate well. So for ammonia, which is which perform best out of the three gases in terms of friction, it actually also have the lowest wear as well. And the carbon monoxide is the one that performed second best in terms of friction, and is also have second best in terms of wear. But we can see that they are both of them are performing better than carbon dioxide and nitrogen. So why? I mean, this number, if you look at it, would have suggested that these gas must have interact with the surface, potentially form some protective film, and that's why we can have low friction and low wear. So what we did is that we actually perform XPS to find out what is the chemistry on the surface. So this method allow us to look at the top 10 nanometer of the surface. And here I show you the result for the surface that is formed in ammonia. So the important takeaway is that there are a peak here which correspond to the formation of metal nitride, and then there is also another peak here which suggests that there is some absorbed ammonia on the surface. So what it is telling us is that perhaps because of the formation of this metal nitride, and also because of the adsorbed ammonia, these two together are basically allowing the formation of a tribal film and reducing our friction and wear. So let's take a look at what happened in the case of carbon monoxide. Carbon monoxide is the case where we also see relatively low friction and very low wear. In the case of carbon monoxide, if we look at the chemistry of the surface, what is interesting is actually the peak that is shown in pink here. This peak actually correspond to the formation of metal carbonate. So in the literature, there's some work that suggests that carbon monoxide can form carbonate. So these carbonates may be the reason why our surface can have reduced friction and wear when it's exposed to carbon monoxide. So now that we have some idea that a film has formed on the steel surface when it's exposed to ammonia or carbon monoxide, perhaps you might wonder, how strong is this film? Is it going to stay forever, or is it sensitive to the environment it experiences? So in order to find out how robust this film is, we're going to take advantage of the fact that HPR has has this chamber which only require a very small amount of gas. So what do I mean by that? We are going to do a gas switching experiment. So because the volume of gas necessary for HPR is so small, so that basically means that I could flush the chamber with, let's say in this case, ammonia. And then once the friction is low, so I know that the film has been formed already, then I can flush the chamber with nitrogen. And then I can see how the friction coefficient change. The small volume involved means that the switching take about 10 seconds for the whole chamber to be completely flushed out of the original gas. So as you can see, in ammonia, we form the film immediately. And then as soon as we flush the chamber or the chamber with nitrogen, the friction coefficient increase immediately, suggesting that the original film that we form in ammonia is now removed immediately, and friction is very high. Then when I switch back to ammonia, you can now see that the friction coefficient drop immediately, suggesting that as soon as now the surface see ammonia, the film is formed and the friction drop immediately. So the formation of the film is actually very fast, but the removal of the film is also very fast as well. You can also see that now the friction coefficient, although is low, but now you have a bit more of a spike. It's possible that, you know, during the stage when it is in nitrogen, because now you don't have any, the surface don't have any protection. So, you know, it's more likely that a little bit of wear may have occurred, and that's why it become noisier. What is actually interesting is that, you know, we have the first step of ammonia and nitrogen, and then we go for ammonia again for the film to form. And then when we go to nitrogen, you can see that, yes, we are removing the film in this nitrogen step. But what is now interesting is that you can see that the removal is slower. So you can see that it's gradually getting to the top in this second step. But in the first step, when you see nitrogen, this is actually much faster. So suggesting that, you know, during this rubbing and, you know, forming and rubbing process, the film that is on the surface actually is changing, is evolving in terms of property. And you can see then by the time you go to the third cycle, things has now been stabilized, and you can see that the removal rates are more or less the same in the second and the third cycle and the fourth cycle. And also you can see that, you know, in the second and third and fourth cycle, the friction coefficient in ammonia gas is now more or less the same. So the film definitely can be removed easily. In this case, it does change with rubbing, but it stabilizes actually quite soon. On the other hand, when you have carbon monoxide, remember this is a film which is mainly of carbonate. So we can now see, at least in the first cycle, something very similar to what we have just described with in the case of ammonia. So you form the film very quickly when you see carbon monoxide. The film get removed very quickly when you see nitrogen, and then it reform very quickly when you see carbon monoxide again. But this film, again, like what we have just discussed with the film in ammonia, is actually changing in every cycle. You can now see that the removal of the film for the next cycle is actually slower and slower. Every cycle it goes through. But you can also see that the friction coefficient in the stage where you see carbon monoxide, even though it's still slower than the case with nitrogen, but you know the difference is becoming smaller. So again, it's suggesting that this film actually with time, as you rub, and if when it is exposed to a different environment, we are changing the chemistry, and therefore, you know, the film are evolving. So we have discussed about, you know, the inert gases. We've talked about the carbon dioxide, carbon monoxide, and the ammonia. Let's take a look at the hydrocarbon. So first, I would like to talk about the saturated hydrocarbon. So for the methane, the friction coefficient is high. So this is supporting what is found in the industry, that in the literature, that, you know, methane don't really form a film on steel. it need some catalytic element in order for methane to work. And in our surface, we don't have that, therefore friction coefficient high. So now let's see what happened to ethane and propane. So as the number of carbon, the carbon chain length become longer, we can now see that the friction coefficient want to become lower. You know, you look at the case where you have the C2H6, the gray line. Originally, the friction is about 1, but you know, towards the end of the test, you can tell that it want to go down, but oh, I cannot. Maybe the film has started to form, but then it got removed, and then you know it formed again. So it's struggling, but it does seems like it want to form something to protect the surface. As you go to the case of propane, now your carbon chain length has increased again. You can see that it struggled at the beginning, but after about half an hour, eventually something start to form on the surface, and the friction coefficient has dropped to about 0.2. And I think now with this trend, we can all guess what happened when we have a 4 carbon. In the case of 4 carbon, we have when you have butane, and in this case, we have tried 2 different structure. It really doesn't matter which structure you pick. Both of them actually give very low friction coefficient, and the film actually form very quickly. It take about less than 100 seconds, and this film is formed, and it is stable within the experimental time frame. In the case of the unsaturated one, as I have mentioned at the start, this unsaturated hydrocarbon is meant to be more reactive compared to the saturated one. So it is probably not surprising that they all give low friction coefficient, because if they can react with steel more readily, obviously it means that they will be able to form a film more readily. And for this particular film, it seems like it is good for friction. So if we look at the wear, again, for the few hydrocarbon that we have tested, the friction and wear seems to be correlated. Those with low friction tend to have also lower wear. So here is the few that is the most interesting. You can see that those that are unsaturated and those that are long chain saturated hydrocarbon, they all have low friction and they have low wear. So we can actually check what is on the surface again. So this time, instead of XPS, we use a method called Raman spectroscopy. So I would like to draw your attention to this region in the spectra. This region, the peak in this region usually signify that something that carbonaceous has formed on the surface. So you can see that for the butane, so basically is this here. In some region, you can see peaks in the spectrum, so suggesting that some carbonaceous material have formed on the surface. In other region, especially at the center region, it doesn't look like there's much. So what is this suggesting is that whatever that is formed on the surface, and in this case a carbonaceous film, it is likely to be quite weak, and you can remove it during rubbing probably quite easily. So to have 1 hour of low friction, that would suggest that the film has to be formed and removed during the whole rubbing process. For the case of the unsaturated hydrocarbon, so it's basically this one here. So we have tested many locations on the wear scar, and we see that a lot of them has the signature of carbon, basically suggesting that again a carbonaceous film has formed. In terms of the chemistry, these two films is actually quite similar. What is the difference really here is the coverage on the surface. So in terms of butane, the coverage is not as good compared to the case when you have the ethane. So it kind of makes sense, because this is more reactive, and probably also that the the formation pathway of this film may be slightly different because of the fact that this is unsaturated, and this may allow it to form film more quickly. So we're going to do the switching experiment again to work out if to work out the property of this film. I'm sorry, it has frozen. Okay, so we're going to do the switching experiment again. So this time we form the carbon-based film on propene, and then we switch to air, and you can see again that this film actually get removed very quickly if it is exposed to air, but it forms very quickly as soon as it's exposed to propene. So it's basically suggesting that whatever that is formed in propane, as soon as it sees air, it got removed during rubbing in air. So you may ask the question of, because of the fact that this high friction occurred during rubbing in air, is it because of air or is it because of rubbing that the surface is being removed? So in order to find out, we run another set of experiment where the switching are done between propane and nitrogen. And now you can see that actually in nitrogen, the the removal process is a little bit different from the air. So I draw this arrow here basically to help us see how fast the film is being removed. You can see that in nitrogen, as every cycle that go by, the rate of removal is actually dropping. So it's almost like when this film is formed, if it is exposed in nitrogen, it actually becomes stronger with time during rubbing. So what is suggesting is that if you look at this compared to what I've just shown you with with the propane oxygen switching, oxygen actually play a very important role in terms of removing this carbonaceous film that is formed in propane, and this actually matches with what we have found in our earlier work looking at hydrocarbon oil as well. Here is just a quick summary of how our steel-steel contact behave in various gases. We can see that in some gases, it seems like the steel-steel contact is performing much better compared to other gases. And I've highlighted a few gases which is of interest, for example, like ammonia, and also, for the unsaturated hydrocarbon, they seem to have some lubricious effect. So you may ask, what can I use this information for? I mean, am I going to, need to put my moving parts into ethane if I need to run it dry? I mean, maybe, but I mean, you may not want to do this. So how are we going to use this information? So I'm going to show you an example of how we can use this information. So we are going to use this knowledge from that piece of work on a scenario where, our contact will see hydrogen. So there's now a lot of work focusing on the use of hydrogen for IC engines. So here is just an example of how it may look like. And in these cases, the pump and the injector will need to be lubricated. And we have shown you that hydrogen is actually not good in terms of steel-steel contact. We know that hydrogen actually give very, very high friction. So that basically means that if my contact is going to see hydrogen, I need to do something. I need to do something to reduce the friction, and where otherwise, the pump will cease, and then, that's the end of the story. The previous work showed that some gases actually can be potentially lubricious. So what if we could add a little bit of this lubricious gas into hydrogen so that, so that these lubricious gas act kind of like an additive. Therefore, my rubbing contact will work in hydrogen. So this idea of using gas as an additive is not new. So the idea, this idea has been called a different name previously. So some of us may be aware of a lubrication strategy called vapor phase lubrication or gas phase lubrication. The idea is quite simple. So you have a gaseous molecule that are lubricious. So you use a carrier gas to bring the lubricious additive to your contact. So here is just some work showing that people have looked at the possibility of using hydrocarbon or using phosphate ester additive, using alcohol as the lubricious additive. And a lot of time the carrier gas will be either inert gas or nitrogen, and there's also some work that looked at nitrogen and hydrogen mixture. But as far as we know, there's no work that looked at using hydrogen as a carrier gas. And so we would like to use this as an opportunity to find out if we can use a lubricious gas as an additive to lubricate contact that is surrounded by hydrogen. So these are the gases that we try as the additive. So the choice here is basically guided by the piece of work that I've just shown you. So we already know that the uh, the unsaturated hydrocarbon actually work quite well. We have seen that ammonia possibly could work quite well. Others choices, for example, like the amine, we picked the amine actually because we know that amine can interact with steel quite strongly based on our research on friction modifier and stuff like that. And and also it depends on whether we can find this easily. So anyway, these are the choice of additive that we tried. In order to do this experiment, now we need basically two gases getting into the chamber. So one of the gases is hydrogen, and the other gases is basically what allow the additive to be added. So they are mixed in advance before they get to the test chamber. So here is just a reminder that hydrogen is it doesn't do well for steel contact. We can see again that the friction coefficient is very high. But now let's look at what happened when we use carbon monoxide and dimethyl ether as an additive. So you can see that actually for carbon monoxide in this case, it actually doesn't work. Even though in our previous work it does show some effect if you have 100% carbon monoxide. In the case of the dimethyl ether, if you have relatively high concentration of dimethyl ether, you can have a reduction in friction. However, as soon as you reduce the amount of the lubricious gas or the gas additive, then you can see that the beneficial effect actually go away. Now you have a friction coefficient very similar to what you get with just pure hydrogen. So with the unsaturated and saturated hydrocarbon, this is exactly what you expect. I think based on what we have just discussed, the saturated one, it has no effect. Whether you add it or not, I mean, you get a high friction coefficient. However, when you have the unsaturated one, and we know that this one is more reactive than the other one, you can see that the friction coefficient is very low, even if you add 5,000 ppm in the system. If you reduce it to 1,000 ppm, you can see that for ethane, it actually struggle. It has no beneficial effect anymore. However, for ethane, you can see that it struggle initially, but eventually it form a film. So you can get some benefit even with 1000 RPM, 1000 ppm, but higher concentration give you a more robust performance. So you may wonder, now that we only have a small amount of this additive gas on the in the system, does it mean that the chemistry of the coating has changed? So here is just to show you that it didn't change. So despite the fact that we are now having a mixture of ethane and hydrogen, the chemistry of the protected film on the surface is the same. It's still carbonaceous base. For ammonia, you can actually have good friction reduction result. Even in the case of 1000 ppm, your friction is low. However, when you drop to 500 ppm, then now the benefit is only marginal. So if we look at the amine gas, and as I said, amine is chosen because for those that are working on friction modifier, we know that amine is in oil is a good friction modifier. So we thought perhaps in gas it will work as well. So it actually worked as expected. You look at these two amine, and especially the diethyl amine, you can see that even when you only have 500 ppm, so that actually is the line in light blue and is all covered by the other line. With 500 ppm, it works. And even with only 100 ppm, so is this like brownish, light brown line, with 100 ppm, actually it works. So even with such a low concentration of additive gas, your contact remain experiencing low friction. And we can look at the surface again, and we can see that despite the fact that you only have a very low amount of additive gas in hydrogen, but the chemistry of the tribal film on these surfaces is very similar to what we have seen when you have 100% of ammonia gas, and so it does, the chemistry of the surface doesn't seem to be much affected by the concentration of the additive gas. So long that they can form a film, the chemistry is more or less the same. So here is just to highlight that, again, the amount of additive gas, if you use amine, it doesn't really need to be a lot. 100 ppm is what you need. You already see a very strong effect. Anything above it, you will still get some benefit, but it's marginal improvement. So finally, I just like to conclude. I hope you are convinced that the atmospheric environment, that the tribological contact experience is actually very important in terms of whether it will experience high friction or wear. We have also seen that if the gaseous environment itself is not good for your contact, there are ways to mitigate it. Some people may choose to use coating, but here we give you an alternative. You might be able to use an additive gas, which are lubricious, and by doing so, you can reduce friction and wear. We have also identified some potential lubricious additive that you can use. And for amine, in the case of hydrogen, the amount you need is actually very, very small. So with that, I would like to stop, and I'm happy to take any question. Thank you.
Thank you very much, Janet. So I think what we'll be doing is we'll be moving on to Kieran's presentation now. So if and we'll swap over. We do have a good number of questions in the chat, so we'll get to those afterward. Yes. Yeah. For audience info, whilst Kieran's getting his slides set up, I'll be releasing the highlights during his presentation, and then, as I said before, the attendance will be released at the beginning of the Q&A. Okay. Janet, for now, can we both leave stage, please? And then we'll let Kieran do his presentation. I'll welcome everyone back on stage afterwards. Please take it away.
Brilliant, thank you. Hello, everyone. And thank you very much, Sam, for the introduction. And thanks also to Janet for sharing lots of really, really interesting insight into the impact that alternative environments have on friction and wear in gaseous contacts. So as Sam mentioned, my name is Kieran, and I'm an applications engineer at PCS. And I have the pleasure of providing you with some more information on our solutions, no plural, for fully controlled atmospheric testing. But first, starting with the briefest of overviews of PCS instruments, we design and develop tribology and fuels testing equipment and have been doing this for a while now, almost 38 years, from various different locations around London in the UK. And during this time, we have installed over 3,000 instruments in over 100 different countries, and are very proud of the vast amount of research on everything from fuels to food that our instruments have supported. And this is what our current instrument portfolio actually looks like. As you can see, we have a range of rigs for characterizing a wide range of tribological phenomena, from rolling contact fatigue to the effect of electric potentials, or measuring lubricant thicknesses at high speeds, and so on. But the two solutions that I'm going to focus on today, and that I think will be highly relevant to those interested in the tribology of alternative environments or atmospheres, are the HPR, which Janet did a great job of introducing, and the MTM-CC. The latter is a brand new accessory to the MTM and MTM-EC that enables rolling sliding contacts to be evaluated within a climate-controlled chamber. I believe this is the first public mention of the MTM-CC, so this new accessory is very much hot off the press and one that we are very, very excited about. But starting with the HPR first, and yes, Janet did a fantastic job of introducing this rig and has done some fantastic work on it with her colleagues at Imperial. And as you can see here, the HPR advances our well-known and highly trusted HFRR instrument to include a fully sealed chamber in which fully automated high-frequency reciprocating tests can be performed within gaseous, vacuum, and/or pressurized environments. This fully sealed chamber comprises of a upper and lower section, which both sit on a heating block. And just like the HFRR, we apply a static load by hanging weights from the halo type structure around the upper chamber section. And as you can see here, we have multiple fittings that connect the sealed chamber to the mechanical unit. More specifically, these include a gas inlet valve with a digital pressure sensor, so that you can monitor your pressure values within the PC software, a gas outlet valve, plus a burst valve and a pressure release valve. And we've taken immense care to develop an instrument that is safe to use within a lab environment. And as highlighted here, the HPR includes multiple software and hardware items to ensure that pressures can never exceed dangerous levels. So this upper chamber section cleverly utilizes a stainless steel bellows system, which connects the upper specimen holder to the vibrating mechanical unit, enabling a reciprocating motion to be performed. Additionally, we've taken great care to ensure that even when testing under pressure, the specimens will not be affected by this and will remain in the correct sort of vertical position, and the desired load will be applied consistently throughout testing. And as this tech spec shows here, we have mostly been able to match the operating conditions of the HFRR, whilst also allowing vacuum to 10 bars of pressure to be applied. So another great feature of the HPR is the ability to remove the pressure chamber from the instrument. This allows ball and disc specimens to be fitted to the upper and lower sample holders, away from the instrument. It also means that gas blends can be added to the chamber whilst also away from the instrument, resulting in much finer atmospheric control. And there are also several configurations of the chamber which allows dry contacts, liquid lubricants, and gases to be tested in a very, very flexible way. And it's still very early in the life of the HPR. It's incredible to see some of the fascinating research being carried out by Janet and the team at Imperial, as well as various different institutes around the world. And it's also very exciting to think about the possible applications where the HPR could also be incredibly valuable going forward, such as the ones listed here. So moving on to our newest featured accessory, the MTM-CC. This is a climate-controlled upgrade to the test pot, which enables tribological effects of gases to be studied within rolling sliding contacts at ambient pressures. The MTM-CC features standard size inlet and outlet ports, which allows a controlled flow of gas through the MTM pot. And we've ensured to use high performance materials like CalRes and fluorosilicon seals for maximum gas compatibility, as well as a highly flexible ball shaft seal, which we like to call the lollipop seal. And this prevents leakage without importantly affecting traction measurements. This new accessory opens up a realm of new testing capabilities for existing and potentially new MTM and MTM-EC users, including the evaluation of lubricant performance under controlled environmental conditions, friction and wear in inert and reactive environments, the lubricity of gases under dry or lubricated conditions, as well as some of the great work that Janet's been doing on the impact of gaseous additives to frictional performance. Additionally, we've made sure that the MTM-CC can still be used with the slim mapper, so that the influence of controlled atmospheric conditions on the evolution of boundary additives can be studied. And more generally, we've worked very hard to ensure the MTM-CC is compatible with as many of the existing and most popular MTM accessories and features. Some of these include the slim mapper, as I just mentioned, the EC module, which enables electric potentials to be applied to the contact, cooler low load kit for testing under 10 newtons, and reciprocating kit for oscillating movements, etc. So just to conclude, and as I just mentioned, this accessory is very much brand new. If you'd like to learn more, please do go visit our website. Please feel free to get in touch. We're always happy to have a conversation. And if you'll be attending the STLE annual meeting and exhibition next month, make sure to stop by our stand, where we'll have both the MTM-CC and HPR with us too. So thank you very much for listening and attention.
Fantastic. Thank you very much, Darren. Yeah, really, really interesting looking capabilities on the equipment. So that's great to see. So now we will move to the Q&A portion of the event. So as promised, for those who desire it, the attendance certificate is now available. So please go ahead and click on this to download it now. It will only be available now during the event. Janet, could I please ask you to return to the stage? Thank you very much. And we'll take a couple of questions in about 5 minutes. So we'll get through as many as we can. One thing I just wanted to ask before we proceed, Janet, are you happy for me to forward any questions on to you afterwards, and then we can reply to reply to anyone that we don't get time?
Sure, no problem.
If that's it, thank you. Thanks. Just there seems that there's quite a few, so I just want to check that. So we have more of a comment, I think, just a clarification here.
Yes. So I did make a mistake. It's nitride.
Okay.
Well spotted. Well spotted.
So points for Matthias. Thank you. Yeah, thanks for that. Yeah, thanks for the comment there, and yeah, good to clarify. So we have another question here from Narendran. I hope I'm pronouncing that correctly. But who asks, do we take into consideration the deformation to the surface due to heat generation during any of the frictional tests?
So that's actually a very good question. Obviously, you rub it dry, so frictional heating may be an issue. So we didn't do the in situ measurement in terms of temperature, but we did the the estimation. The estimation, the worst scenario where the friction coefficient is 1, is 61 degrees. So the test is at 25, so plus 61, so it's 86. So I don't think that will be an issue in our case. I hope I have answered your question. So in a sense, we did the prediction of temperature rise, and we decided that we don't need to worry about it.
Okay, thank you. We have another question here from Shin Shui. I hope that's correct. But and they ask, the test load of 200 grams looks quite low. How about the coefficient of friction / wear change under higher load conditions?
I think because I mean we didn't have time to go through all the details, so the pressure actually is not so low. So the maximum Hertzian pressure is actually 820 megapascal. So I mean, you can argue that, okay, the average pressure is only 600 megapascal. I mean, we could do higher low, and obviously it will have an effect, especially in terms of wear. But I think it doesn't change the fact that, the contact perform better in certain gases, and especially for the case of using the gas as an additive, it obviously showed that this is a promising avenue to pursue. So what Chen Xue said is right. The result will depend on the condition, but I don't think it changed the narrative of this piece of work.
Thank you. A question here from David, who asks, I was particularly interested in the data shown on slide 16, especially the information related to hydrogen. Has this data been published yet? I'd like to reference it in our work.
So both piece of work, this is 2 pieces of work. So I have put the reference on the chat. So feel free to download them, and they have my contact info. So you can always ask me question about the paper after.
Well, that's fantastic. Thanks. And for anyone else that wants to go back and sort of review anything, you will all receive a replay of this event. So you'll be able to pause at any point and look at the references in the slides. Okay, we have a question from Aladdin, who asks, from your understanding, what are the best lubricants that you can put, I think that's what you could put or use in a hydrogen combustion engine?
I can't say because we are testing. So Aladdin, I hope that in a year time you will see a publication about that. But not all of them work, and not all additives work. So we do have to do some tweaking.
Thank you. Question from Chris here, who asks, how would the use of additives affect ignition and combustion of hydrogen and the emissions from said engine?
I don't think emission will be a strong effect, just because we can actually use only very little. However, one good thing, Chris, is that we do have a hydrogen engine in Imperial College. So the plan basically is that at some point we will try this with a hydrogen engine, so that we will have actual data to show whether it has an effect in terms of, for example, the spray, not the spray, sorry, the combustion, and also probably on the other lubrication and stuff like that. But this is something that we intend to do.
Okay. Great. So with that, we are at our 60 minutes allotted for the session today. I think there's a couple of other questions, 2 or 3 other questions, so not too many. Janet, I'll when I sort of follow up after the event, I'll send these to you so you can if you could take a look at them. Please, thank you very much for doing that. So with that, let's draw our event to a close. So I would like to, of course, thank both of our speakers today. Thank you very much, Janet. Fantastic presentation. Lots to think about. Lots of reading for me to do as well. Great to have the references. Yeah. Thank you very much, Kieran, for the presentation from PCS Instruments. Always great to hear about the newest innovations in testing equipment. And great to see all of these new modules to help tackle upcoming challenges in tribology and in industry in general. But thank you very much as well to PCS for the partnership here for today's event. As I've said plenty of times previously, we wouldn't be able to do this without our partners. So thank you very much. As a reminder, Surface Ventures are we're running events every month now, so please do visit our website. You'll be able to see latest upcoming events. Do check out our LinkedIn as well in terms of next event. I can now share the registration link for that. So this is Professor Andreas Rosenkrantz from University of Chile, who will be presenting on 2D vaccines. So that will surely be a very interesting talk as well. So please go ahead and click on that. That will be available on our website soon. Do check out LinkedIn for our fortnightly newsletter, Modern Surface, the next edition of which will be released tomorrow. And as a final note, if you know anyone, any of your colleagues or friends that will be interested in these webinars, please do take the time to send the webinars, send our information to them. It'd be great for us to keep growing our audience and sharing this information with more people. So thank you all very much for your time today. Thank you very much to both of our speakers, Janet and Kieran. It's been great having you.
Thank you.
Thank you.
Thank you all very much. Have a good day.